Hello, uh, welcome for joining me at this presentation at Parity. I'm very happy to be able to do this in this remote way. I would like to talk to you about quantum machine learning and in particular about the quantum Boltzmann machine. So, as you undoubtedly have heard is of the successes of machine learning. I just list here a few examples, which is the AlphaGo system, which was the first computer system that was beating the world champion to play Go, based on deep neural networks and a lot of simulation of self-play. And the other is a system that recently came out. It's the Agents 57. It's also by DeepMind, and it's a system that can play a large suite of computer games at superhuman performance, also based on the deep neural network here envisioned, where the input is the screen of the system, the screen of the game, and the output is the joystick movement. Now these kind of applications are very impressive, and as I said, they have superhuman performance. And in order to get that performance, you need models with a large number of variables, which are very complex to train. And so the bottleneck seems to be to get the performance is largely an issue of complexity, and that's where the quantum aspect may be coming useful. So indeed, one could say that machine learning is actually all about probabilities. So most of the machine learning models, whether it's a clustering model or whether it's a supervised method or an unsupervised method, can be formulated as some sort of a probability model which is parameterized by some parameters, and then the parameters are adjusted in such a way that this probability model does the thing that it needs to do. So for instance, here in this example, we see an example of an autoencoder that maps an input to the same output through a bottleneck. And this can be seen as a very large probability model where each layer represents thousands of variables. And in order to compute in this model, you need to compute so-called marginal statistics, which are expectation values of single variables or correlations. And the computation of these correlations is highly non-trivial because of the non-linearities in a model. So one can view this as sort of a stochastic system with a very rugged energy landscape, and so formally the amount of computing that is required is intractable and scales exponentially with a problem size. So one typically resorts to sequential methods such as the Monte Carlo methods, and so at any time the system is in one particular configuration, and all these configurations have a certain probability where the states are configurations are S and the probabilities are Q of S. And so in order to compute an expectation value, in a sense, all the states must be visited, for instance, by sequential Monte Carlo, and we of course know all this story. So for instance, in the case of a ferromagnet near criticality, you have a mixture of up states and down states, indicated here by black and white. And in order to get the expectation of some individual spin or some correlation between two variables, you have to let the system evolve over many kind of states. And here, in fact, the energy landscape is this two-weld, this kind of landscape. So this is very time consuming, and if we could accelerate this would be a great advantage for the machine learning. So what about the quantum situation? So a quantum state of a quantum wave function represents the different outcomes simultaneously. So unlike a classical system where we have to visit one of these configurations at each time, in the quantum state, these different configurations coexist in the physics. And can we somehow exploit that to represent probabilities? So, the idea would be to map a probability distribution to some sort of a quantum state. So we have our probability distribution that describes our machine learning application or whatever, or the data from real world data. And can we define a quantum state that sort of represents this data, and what does that mean? And so if we could do that, then having such a quantum representation would allow us to compute expectation values not by sampling, but by preparing the same state repeated a number of times and doing measurements on the same quantum state. So it would have a different kind of altogether different kind of quality than doing such a Monte Carlo sampling. Okay, so that's the goal. So how can we realize that? So the way that this is formulated in the case of the quantum Boltzmann machine is, so can we design Hamiltonians such that their ground state represent a given data distribution as good as possible. So this is a learning problem. So we imagine having a Hamiltonian, so for instance of this particular form where H is a sum of terms, these are quantum Hamiltonians, and then we can construct a density matrix, and this density matrix is then parameterized by these parameters, and we want to find the density matrix such that it represents the data distribution as good as possible. So in order to set up that learning problem, we have to also put our data into a quantum format, and one way to do that is to transform the data distribution into a rank 1 density matrix. So this is a pure state where phi in the certain representation has a magnitude which is equal to the square root of the probability. So then we have two density matrices. One is given by our data and one is given by our model, and we want to find the parameters such that this rho is as close as possible to this eta. And for this we can define a measure which is called the relative entropy, and then this relative entropy then becomes a function of the parameters in the density matrix, and we can minimize this relative entropy by a gradient descent procedure. And this is called learning in Boltzmann machines and also in quantum Boltzmann machines. So this is a direct generalization of the classical Boltzmann machine, which worked with classical probability distributions, generalization to density matrices. So the quantum statistics you can now define. So we have a classical distribution, and actually we can define quantum statistics for a classical distribution. So if we take this definition of eta on the previous slide, which was this one here, and we plug in the expectation of an operator, which is just a trace of the product, then we get this expression here. So we see where classical statistics are linear in Q, we find that these quantum statistics generalize in that sense. They are quadratic in square root of Q, and they are the same in the case that this operator that we're getting the expectation from is a diagonal operator. So it's a strict generalization of the classical case. So we can use this idea to learn, for instance, a quantum spin model. So, for instance, as a concrete example, consider a Hamiltonian that consists of single node terms and pair terms with arbitrary couplings in x, y, and z spin directions, and between any pair of spins. And so for this Hamiltonian, if you compute the gradients of this cross entropy, they become of this form. So the change in these parameters here are equal to the difference between the statistics computed in the data minus the statistics computed in the model. And the same is for these pairwise couplings. It is given by the difference in the pairwise statistics but in the data minus the pairwise statistics in the model. And so you see that the learning stops if these gradients are 0. So that is when these statistics in these two models, in the model is the same as in the data. So that's the convergence criterion for this learning procedure. So we can apply this to modeling, for instance, in any kind of data. So here I have some data from neural activity of neurons that in the retina of salamander retina. And so you see here time, and you see these dots are the firing of individual neurons. These are 160 neurons, and they spike over time, so they give a 0-1 kind of a pattern. And here you see the learning in action. So the quantum Boltzmann machine is trained over episodes, and so it starts with an S which is large, and then with the iteration it gets lower and lower. It doesn't get to 0 because the Boltzmann machine cannot perfectly represent these data, but it can do a good job. And so it learns, in fact, so as you said, so the target is a rank 1 density matrix, this eta, And it starts out with a row, which is in principle a full rank density matrix, but here it shows that actually the largest eigenvalue sort of becomes very close to 1, meaning that in fact the learned representation is very close to a rank 1 solution. And so, so you find a rank 1 solution close to this, which is similar to this to the data, and you can compute the Kullback-Leibniz divergence, which is the difference in the probabilistic sense, the classical probabilistic sense between the data and the model. And you can do that for both the quantum Boltzmann machine, which is shown here in red, and you can show it also for the classical Boltzmann machine, which I have not shown results here, but you can do the same thing. And you see that indeed that the quantum Boltzmann machine has an error which is much smaller than the classical Boltzmann machine on this training data. But more interestingly, there is also 28 test sets of, of other experiments doing the same thing, and you can see whether the statistics that are learned in the model, whether they generalize to new unseen situations. And indeed, these histograms show the test performance on these 28 other data sets, and you see that the error on this test data, which is on the quantum Boltzmann machine, is also much better than the test performance using the classical Boltzmann machine. So this means that this model, this quantum model, learns quantum features in this classical data set that generalize to new unseen situations. So that's, I think, is interesting. So there is more spectacular differences between classical and quantum learning. So in this case of the parity problem. So suppose here we have the parity hypercube of 4 bits. And so this is a problem in which you want to learn a probability that is larger than 0 for any even parity state. So for instance, like this one. But for any odd parity state, which is any of its neighbors, you want to learn the probability 0. So you have a very difficult distribution where every probable state is surrounded by improbable states. And so it's a very hard distribution to learn. And the classical Boltzmann machine cannot learn this except if you use very many hidden structures. But this quantum Boltzmann machine, without any hidden variable, can learn this perfectly, which is shown here in this graph, where the data distribution is plotted against the learned distribution. It shows a perfect line on the log-log scale, and the classical distribution essentially learns nothing. So in addition to good learning, there is also new features in this in representing classical data as ground state of quantum systems. And so so this transformation that I said that the wave function of the data is represented in this way, with alpha is 0 so far. We can also put an arbitrary phase. And in general, what you can ask yourself, if I have some classical system and I divide it in 2 subsystems, I can compute the mutual information between these 2 subsystems. Now I can also, so that's here, that's the classical distribution and the mutual information between 2 subsystems. I can also map this classical system, classical distribution, onto some quantum state, and I can compute the mutual information then in this quantum state. And what turns out that the quantum information is at least twice as big as the classical information, and that is illustrated in these figures here. So here you see for a random bunch of probability distributions, you see we take a random distribution, we compute its classical mutual information between between 2 spins and a third spin. And we do this, we then map it onto a quantum system, and we compute the quantum mutual information between these same 2 subsystems. And you see that these points are always above this diagonal, which is the diagonal of the quantum information being twice the classical information. So you see it's always larger than that, and it's equal to that if the relation between the 2 subsystems is deterministic. So that means that there is more information in this quantum state than can be extracted classically, and this more information is in fact related to entanglement. So it is known that actually the classical, so as I say, that the classical information is less than C, which is half of the quantum information, but you can of course, change the basis in which you measure, if you want to have this quantum state. So we can go to another basis. Instead of having the basis S, we can go to a basis T. And then if we do an orthogonal transformation U, you can show that there is actually another probability distribution that is governing now the data. And this other distribution, you can compute the mutual information, and you can actually, if you maximize, you take the best U that factorizes over the two subsystems, you can actually saturate this bound of the classical information being equal to C. So that can be done by an orthogonal transformation. But there is a remaining half quantum mutual information that cannot be accessed in this way. And these so-called quantum correlations you cannot capture by an orthogonal measurement, but potentially you can measure them by a non-orthogonal measurement. So, and this relates to the locality problem and the violation of the Bell inequality. So, as a very simple example, for instance, consider 2 bits. You can set up the quantum state corresponding to the 2 bits, and they violate this Bell inequality, or this CH-SH inequality. And so you have here an example that if there exists a probability distribution that measures these statistics A, B, and C, which are the measurements of the 2 spins in different directions, then classically there would exist such a probability distribution that gives the outcome. But if that is true, then you would find that this inequality should hold. But in fact, you find for this system that you can make measurements on these two variables, which are non-orthogonal, such that you violate this inequality. And that is shown here in this figure. So you have the 2 angles here, and you see that everything that is above 0 is violating this inequality. And so here's a point, for instance, that violates this inequality. So this means that actually the quantum state described by this classical data violates the Bell inequality and has issues of non-locality. So the way to resolve this is actually, you cannot describe this by local variables. You need some sort of a non-local description involving the 2 variables at the same time to get to describe the system accurately. So this may actually be interesting. So this is just an example, and this generalizes to larger systems. And so this may hint to that these kind of quantum features, they may enhance actually the classical correlations. These quantum correlations may enhance the classical correlations and may be somehow useful to be seen for future generations for machine learning somehow. Okay, so as the last point, I would like to talk about the intractability. So normally we have a forward problem. Given in physics, we consider Hamiltonian, want to compute some statistics, and this computation is intractable, as you all know. So the learning problem that I considered here is actually the reverse problem. I have some statistics given, I want to compute a Hamiltonian. And the way it's solved by the learning is by a sequence of forward problems. So I start with some parameters, I compute the corresponding Hamiltonian, I compute some statistics, those statistics I put in the learning rule, it changes my parameters, I get new parameters, etc., and I iterate this. And so, since this is intractable, this learning is also intractable. And the way that this can be improved is by various type of approximations. So one is to take a rank 1 approximation, doing a variational approximation. This is something that we're considering at the moment. Something else is in the direction you can work in. We're working on various ways in the direction of quantum belief propagation. So it's a sort of approximate inference on these problems, which is more which is also a very promising approach. And lastly, of course, this work should hopefully benefit from some quantum hardware, whether it's some D-Wave-like device or maybe a quantum circuit. So in this last direction, the quantum circuit, we have done some initial work where we use the idea of a quantum variational eigensolver. And the feature of that is that it can do the intractable computation, which is for a given parameter, for a given wave function, compute the expectation value, the Hamiltonian, the eigenvalue of that, this quantity here. This can be done in a tractable way in a quantum circuit. So this you can use as part of the quantum Boltzmann machine learning. And here we have shown our first results on that on this same salamander retina data using this quantum circuit. Of course, this is still in simulation, and this is very much in progress. We have all these peaks here, which are probably due to level crossings in the spectrum of the Hamiltonians that we learned. There's a big story there, and I don't want to go into details about that, but it shows that you know, there is some way to map this learning problem onto a quantum circuit. So as the result, so the physics-based machine learning is the motto. So if we want is to let the quantum physics work for you, and I advocate the idea to use the wave function to represent the probability distribution, and therefore try to get another way to the intractability problem of that is faced in large machine learning applications. So I've shown that the quantum features can also improve the machine learning. So we get better models, such as in the Parity Problem, and we get better predictions, such as in the salamander data, and we go beyond probability. So we can use non-probabilistic features, such as entanglement, as I showed with this Bell example. And of course, we are still we are in a need for physical systems that can compute these quantum statistics for large data sets, and so this is I think the thrust for the future. If you want to learn more about this paper, about this work, I have this paper that you can download from the archive, and it was recently published in the Journal of Physics. As an end, I would like to have a short announcement. I am organizing an ALICE workshop on quantum and physics-based machine learning. You may know that ALICE is a European initiative for, it's called the European Laboratory for Learning and Intelligent Systems, and it unites the best machine learning research in Europe, and you can find more about that on the website alice.eu. There are 11 ALICE fellow programs that are active in different topics in machine learning, such as medical data or robotics or computer vision. And one of these programs is on quantum and physics-based machine learning, which is the one that I'm heading together with Riccardo Zecchina from University of Milan. We have a meeting, which was supposed to be a real meeting, but will be online meeting with about 28 contributed and invited talks on 6 to 8 July. And it's on various topics of quantum machine learning. And if you are interested, visit this website and you can learn more about it. Thank you very much for your attention.